So I do this demo every year, and I've got about 45 minutes to do that. I'm going to spend about 15 minutes just going to the 20-meter site to show how that works. If we were at Green Bank, the actual radio telescope is outside the room where we meet, and you can actually see the telescope move. And then the rest of the presentation, about 30 minutes, I'm going to talk about raster scans. So I try to vary these demos every year a bit, concentrating on different aspects of what you can use the 20-meter for. So pulsars was one of the prior demos that I did. So I'm going to basically two shares on my screen, first the Skynet site and then the PowerPoint. So let me see if I can do that. Oh, I'm sorry. I've got to, let's see, there's the share screen. And how do I find the, I clicked on share and I'm only seeing iPhone, whiteboard, and screen. Now, maybe I've got to do screen. Let me see if that works. Let me see if I can bring up this. Can you see the Skynet page?
Observe the night sky. We see
it. Great. Okay. Looks like it automatically went there. Some of you have probably seen this before. I spent, see, last month we had an RTOP session on this, about a couple hours. It was very fluid, kind of open questions. This is a little more structured because I've got to get through a lot in 45 minutes. So what this is, anybody who's a SARA member, any US citizen can get onto Skynet. If you want the password, just email me. I'll email you back a statement that you have to agree to, and it's basically you are a U.S. citizen and want to use the 20-meter telescope. That's by an NSF grant. They have that requirement. You also have to agree to you'll only observe non-man-made astronomical sources and objects and not provide telescope access to any other individual. So I'll be going through that and the types of things you can do with this. So let's have a look at this. If you don't sign up, you can still look at all the data from Skynet, and I'll show you some links later. So we go on to radio observing. This is the page where you're going to want to, Skynet also has a number of optical scopes, but for our account, it's just radio. And there's only one, the one at Green Bank. There is a future grant to expand that to 8 additional scopes around the world. So that'll be exciting. To add an observation, for example, this is very easy to operate. It's ready-made for you. The hardest part is the interpretation of the results. So that's the rest of the demo on a particular aspect I try to cover. Add a new observation. You have to key in your an object to look at. So let's just pick something that's on the globe. I see 3C147. 3C147. It'll search for it. It finds it. What we ask members to do is to put their initials after it so we know who's using what in our account. You can adjust the elevation that you want to see that. Currently it is visible. So everything is good on this page. You go to the next. There's only a few pages here to complete. You have the option of observing in low resolution. If you do that, you can, and your object happens to be a pulsar, you can click pulsar mode. You'll get a different printout for that. Low observation, you have a low resolution. You have a choice of different filters. hydrogen 1 or the 2 hydroxyl groups, which you'd want to do, for example, for astronomical masers, or you can get the whole L band here. If you were to go to high resolution, for example, you want to look at some of the spectral lines, masers or hydrogen 1, you could set your own frequencies. So you can do that. You can save and continue here. At this point, then, you're picking what type of observation you like to do. This shows you the number of credits up on top, which are the number of seconds that are left in the account. Track and on and off are very same. As the name implies, you're tracking the object through the sky for a particular time period. On off basically tracks the object and then goes off object maybe a degree or two in hopes of subtracting some of the background that's not very useful if you're observing in the galactic plane, but that's the thought process there. Mapping and DAISY are very similar. You have a basically and that's today's discussion topic. The telescope is slewing back and forth and making the radio image around your particular target. DAISY is just a circular petal pattern. So if you're picking map, raster scans can, if you accept all the default values, they can be somewhat expensive, but there's ways to reduce that cost. Was suggested if you put in 6 beam widths, and let's see, it should give you, you could select this, integration time, slew speed. You can change the gaps along the sweeps. And there you can see it estimates the number of time it would take, in this case, 4.5 minutes. You can save that and continue. And then if everything looks good, you can then say submit, and then it will observe the target. And it's usually immediate. You don't have to wait very long. There's really no queue here unless there's maintenance being done. I'm not actually going to select it, actually send it, submit it. There's just plenty of examples there. I'll save the time. So it's that simple. But once your observation is done, you can go to the observation page. It would be sent here. And these are all different observations completed. So if we went one farther back, you can see I had one of, in this case, a tracking example. Let's take that one, Cassiopeia A. You say that was the observation I just did. It'll say you can now view your data at this location. I would bring it up, and then I would get my observation here. You can use this observation number to find it at any time on their log, but you can see the, this looks like I was doing H1 observing in Cassiopeia A. You can see the both the emission and absorption lines here. You've got a couple different views of it. You can look at the raw data in case you wanted to export it or do anything of that sort. If you wanted to look at 20-meter info in general, this is a very useful page on the SARA sections. I've got a link to it. You can search different projects by date, by the name of the source, or by the user. That's useful if you're looking at work by other people there that happen to be experienced. You want to see what they're observing. And of course, you can, there are some instruction books here, observing advice. You can look at that. This takes you to the screens I just mentioned, gives you a little more details. There is other documentation on the site. In addition to these, I've posted all my PowerPoint demos from the last few years on the analytical section, so you can see that as information. One of my favorite scientists I like to follow, Dr. Reichart. He oversees the Skynet program. He's written several papers on the 20 meter. He takes it to a very professional and advanced level. So if you really want to get into what the 20 meter can do at that advanced level, read his papers. In my PowerPoint, I reference his work many times. If you want to look at all the logs of the entire log of the 20 meter results, you can go by year and just search through these things, and not just by SARA members, but the whole 20 meter community. I do this usually if I'm working on a project. I want to see what that target, what the data for that target was by other observers before I do my own to see what worked. So this is a very good page, and that is fairly straightforward, and that's what we'll look at. So let me see, that is about, let's see if there's anything else I want to say on here. That covers, I think, going through the 20 meters, so actually quite easy to use. The next thing I'd like to do is then give you some examples of raster scans. And the next thing I brought up on my laptop is the PowerPoint. Can you see that, or are you still, everybody's still on the Skynet page? Okay. Good. Let's go through that and find some can get into trying to get this slide and dwell on it. I like to be more of a reference for you afterwards if you like to explore raster scans. But I will stop at an appropriate beginning. We talked about the search box, and I kind of put two scientists down that I like to follow. One is Dr. Reichart. So if you wanted to see what he was doing, or maybe some of the input data he used for his papers, that's how he goes by user. The other one I like to follow is Frank Gigo. That's how he is in the system. He's one of the scientists there at Green Bank. And for example, when I did a search for Frank Gigo, he had this object repeated several times, OJ287. I didn't know what that was. I looked on the internet, and there was a, let's see, there was a sky and telescope diagram there of OJ287. Apparently it's a binary black hole, and as one black hole plunges through the disk of gas, there's a flare event. So I think that's what Dr. Giegel was searching for, is at that particular time. Happens every 12 years. So you never know what you find there. So let me go into now some of the what I find on the raster scans. So every year when I do a demo, it's kind of what I've been investigating for the last few months prior to the demo. And this year I've been looking at raster scans and trying to understand them a little better. I results. I kind of as a hydrogen one. I was surprised that a lot of it is satellite software imaging artifacts, and I'll point out some examples. I think to keep in mind, I think, is I'm going to have a slide on this, but it shows what the antenna pattern looks like for the 20 meter example pattern, and you can't see detail within that within the beam width, and be mindful of the field of view that you're looking at, and these may be obvious things, field of view, but a lot of beginners often overlook it. They're not aware of it, and then when they realize that, it becomes obvious. So let's see what we have here. So these are I think the comments here. It's important to, I've got an image here of a beam pattern, main beam, and this is not a solid boundary, but a schematic to help you visualize this. When you're observing in radio, it's not the same as in light. A lot of people think of light going through the telescope, parallel rays, the particles hit a camera, your eye, and you see it. In the case of a radio beam, it's a little bit different. And that antenna pattern is, I've got a note below, the antenna 3 decibel beam width is the angle between the half power of an antenna pattern or beam over which the relative power is or at 50% of the peak power. So that's an important concept to remember. If that 50% was changed to 40 or 60, for example, that would change, but it's based on 50%. And that's like a 1 pixel beam when you have that raster scan. Going back in 20 meter, we have 2 receivers that are placed on it. For most of the time, it's the 1.4 gigahertz receiver. That's the L band, and the beam size is 44 arc minutes. So that's quite large. Anything within that beam size, you can't see structure within. But it's an L band that you can do the H1 and the astronomical measures, the OH molecules. So what's in the 8 to 10 gigahertz receiver, when they put that up, very rarely do they put that up. And when they do that, the good thing about that is you get a smaller beam size, 7 arc minutes. And that can show a little more detail on large objects. So I found we'll look at later, an image of the sun, which is about half a degree in size, apparent size in the sky. So this means that the beam size is less than the size of the disk of the sun, and that means you might be able to see some structure. So the thing, I didn't take this particular observation, but I think it was a solar flare from everything I could determine from it. So we'll take a look at that. So this is a very important page. Read it, and if you're new to radio astronomy, let this sink in. Here is some basic tips. What can you see with deep space objects? Well, a lot of objects fade with time, like Cassiopeia A. It fades actually through the decades quite rapidly. It's now the second brightest object in the sky after Sig A. You've got pulsars that slowly change with time. You have masars which vary with time too. So that is why we're interested in that. Here's a reference I made to one of Dr. Reichert's works. You can look that up. His papers are on the internet for free. You can look at them and read them. I put this in here on signal drift because I think sometimes we get that with the 20 meters, so it might be useful. So let's take a look at some of these deep space object raster scans and how to interpret them. So these are my opinions. I would go into the log of results if there's something I wanted to see. Sometimes, and after I look at them, I may or may not take my own target, my own observations at the same area, but I have to interpret them somehow. And if you're new to this, it's not so obvious. Here's one. Next one here. Here's one. I just found this observation in their SIGX. It's a black hole. Obviously, the black hole you can't see in the optical or perhaps the radio. But the object on the right is a optical image of the location of SIGX-1, and near it is this Tulip Nebula. You can see it's a bow shape object with somewhat of a dark band in the middle, not as intense. And you can then see here the radio image of the same area. It kind of looks like a bow shape with a not so intense in the middle. So this happens to be a coincidence. In fact, it happens quite a lot when you compare a radio object image to the optical. And you can see here, obviously, it's not the same image because in the optical, the Tulip Nebula is 16 arc minutes by 9 arc minutes. And whereas in the radio, you have several degrees from, let's see, 36 to 46. So the radio image is a very large area of the sky, whereas the field of view in the optical image is very, very small. So it's just coincidence they look like that. That's not picking out one. It just seems to happen a lot, and we'll have more examples of that. So you have to pay attention to these, your field of view. It's very important for that. The other thing to keep in mind is if you ever used an optical scope, a professional scope, as well as amateur scopes, when you slew to your target, it's not necessarily right in the center of the field of view, obviously, because your field of view is quite small and it might be off a few arc seconds, a few arc minutes, and then you take the hand control and center it. In a radio image, you have such a large field of view, it will always be dead center in there. That's important to keep in mind too. Here is a raster scan. Someone's looking at SAG-A. Here we have two different observations of it. Obviously, they didn't put the, I don't think they put the coordinates for SAG-A in there because that would be right at the center. I think what they were trying to do was get a very large field of view of the galactic plane. So you have to go into these raster, the raw data to see exactly what somebody was looking at. Here's one, the Great Rift. Someone's doing the mapping. I thought that was an interesting concept. I kind of took it for what its name was. The Great Rift, you look at the optical, it's a dark band of dust, the Milky Way. They seem to have captured that. Here is one. This is one of my observations I did in the past. Hydrogen-1 is everywhere in the sky, so it's you will always find that. And I learned of the Lockman hole in the northern hemisphere, the Chandra Deep Field South for the southern hemisphere is very similar. It's a place with very little hydrogen-1 and dust. And if you look at the peak 420 on this, that is the smallest hydrogen peak I ever saw on a radio telescope. I called it a rare nothing because if you point it anywhere else in the sky, you will find it there. And you have to realize that sometimes if you're pointing at something in the sky and you get a hydrogen peak, but your target really has no hydrogen in it, then you're looking at the hydrogen behind it. So, for example, if you pointed the telescope at Pluto, you're going to see a peak, and that's not from Pluto, it's from the sky behind it. Here are some, I'm not going to get into the examples too much. You have Orion A in M42. This is a typical image you may get on the 20 meter. If you look at some of Dr. Reichert's work with his parameters and his processing of it, you see a lot more detail in here, which I thought was very interesting. He captured Barnard's loop. So he's got a lot of materials on his website and in his papers on how to use this scope at an advanced level. I won't say too much of this. This is the Rosette Nebula. The apparent dimensions are actually very large, 1.3 degrees. So the radio map corresponds with that. How do I know? Because if you look at the number of degrees in here, it's about 1.3. So they do correlate. Here's one of M8 and I'm sorry. I'm trying to M8 and M20. Here's the corresponding area. This was dead center on M8 for the what I said earlier. This is an optical image. The maps probably don't compare because of the field of view and the center of the image, but it's in that same general area. One for Virgo A. Again, take a look always at the field of view. I've got part of the share screen covering up the field of view, but I think from memory is about 9.8 minutes field of view. So you can look here, it's in degrees. Now, the other important thing to keep in mind, you'll see this little circle on all the raster scans. Now that is your beam size. So basically within that beam size, you're not going to see any structure. That's why something as small as Virgo A may come out a little bit larger here. You can see it's at least a whole degree when it's actually optical size is smaller. So as the beam is slewing back and forth, you got the center pixel, probably right dead center is the Virgo A radio galaxy. And then as the beam moves off, you've got the side of the beam picking up some of the, well, the side of the beam going through the center of Virgo A. That's my interpretation on how you have an image like that. Same galaxy, radio galaxy Virgo A. This is work by Dr. Reichert at a more advanced level where he cleans up some of the background and he shows you how to do that. Here's an interesting one because the radio image just happened to look like the optical image. You can see in the optical image Sig A and the two lobes coming out of it, the jets. This is a very small field of view. In the radio telescope, 20 meter, you can see this is several degrees across. Obviously, another coincidence that it just seems to look like it, just happens a lot. So you have to do that reality check, do the field of views, match up. And in this case, no, they don't. They're very different fields of view. And this is just probably hydrogen 1 in the area, and then some imaging artifacts with the software. The box down here is one of Dr. Reichert's observations of Sig A. Now, I was curious about this too, so I did my own observation, but this time I changed the input parameters to actually try to force a different image. So if you do 1/10 sweeps between the gaps, you get a very good image. In this case, I did it purposefully 1/4 beam width. And you can actually see, because it's so far spaced apart between gaps, you can see the beam slewing back and forth and having a different effect on radio imaging. So that's, I thought that was interesting. Here's the Andromeda Galaxy. Andromeda Galaxy in the sky is actually very big. It's about 4 moon diameters across. The moon is 0.5 degrees. Andromeda is about 2 degrees across. Of course, you don't see it 2 degrees in the sky because it's very, very faint. You just see the pinpoint middle of it at about 6 magnitude. But in the radio image, you've got about 2 degrees here. So that is Andromeda. It's right at the center. Perhaps you can be forgiven to thinking this was M110, which is the galaxy below, but it's not. I looked that up. I looked at the coordinates for that, and M110 is not on this radio map. What this is, I'm not sure. I think it might be a satellite, just happened to be caught. It's amazing how many satellites are in the sky. They're everywhere. And if anybody does optical astronomy and looks through binoculars, it's like not a minute goes by that you don't see a satellite. So you see a lot of this. And let's see, I'm not going to go through that. I want to say a few things about solar system observing. So let's go on and continue about that. So what might you see in the solar system? Maybe some eclipses, occultation. If you're lucky, a comet collision in Jupiter. You have the active sun. Planets, you've got the thermal black body and synchrotron temperatures. With Jupiter, it's synchrotron temperatures. It's got a very large magnetosphere. The only ones I've been able, well, obviously the sun and the moon you can get with the 20 meter. Jupiter you can too, though it's near the limits. There's some work by Dr. Reichart to clean up the images of Jupiter. The other planets, really borderline on the 20 meter. I was hopeful that I could see something because there are a lot of submissions by both students and scientists for the different planets, but everyone I brought up, I've kind of went through what I was doing now, the field of view, where do you expect them to be, all of that, and it was something else in the sky. And I'll go through that. I'm not sure if you can pick up other planetary objects with the 20 meter. It'd be really close, and you'd really have to pick your input parameter as well, and maybe choose when the planets are closest. But I haven't seen any evidence in the log of 20 meter observations for that. So I give some tips here. You can take a look at them. Here's the one I mentioned about the sun early on. Notice they got the X-band receiver up there. How do I know? Because you've got the 9 gigahertz receiver on here. These are not my images. I just scanned them. The sun is about half a degree, apparent half a degree in the sky. So it's a little, it's kind of extending past it. I was wondering what that might be. Was that just the side of the beam picking that up, or was it the sun's corona? I'm not really sure, but I thought that's interesting. Here's the one where I saw this very dark object here right off to the side. Again, what is that? 7 arc minutes in X-band? Well, it looks like this, the little circle up here. So as this, the beam pattern, as the beam goes through the disk of the sun, it's possible to pick up some structure. I looked up the day of this observation, and on that day, there was a very large solar flare that was emitted from the sun. I'm assuming that's what you're seeing here coming off the disk. Probably whoever did this observation knew that the sun had a solar flare on that date. They knew they had the X-band receiver on it, so they decided to see if they can actually see something. So that's my opinion of what was picked up here in this image on the sun. There are some very interesting papers on lunar observing. So with the moon, you're picking up the black body temperature, but that doesn't mean it's not interesting. There's a couple of papers I quoted here on the internet. One's by Christian von Stein, who I believe is a SARA member too, and one by Marina Battaglia. I looked at their papers. and there's other information on the internet. As the moon goes through its phases, it actually does change temperature a bit. Nothing to do with the optical light temperature, but it does vary a bit. I was hoping I could find that in the log of 20-meter data, but it wasn't so obvious. I spent some time on it, but I had to move on. So I think this is a great project for somebody if they want to repeat the papers of that I found on the internet on this subject. This is just some general information. There's an example on the Skynet site with the moon, 20-meter temperature calibration example. I was trying to follow this to see if that could lead me to that slight change in the change of the moon temperature. I think the example they used was probably very good data. When I looked at other data, it wasn't so obvious. So I just moved on after a while. I think my conclusions were I couldn't find anything consistent on the 20-meter. Perhaps I needed to adopt a more rigorous methodology. And the other thing I was looking at when I was going through the data was I didn't try to average or add together the different frequency plots and polarization plots. We took everything on their own. So I think that's still a good subject to go back to. Planetary observing. As I said, the only thing that I could confirm on the planets that was viewed was Jupiter. You can see its size here, and it was also helped by a very large magnetosphere. The other planets, I think they're at borderline at best. So I haven't found any evidence that you can see them so far on the 20-meter. I thought this was an interesting paper. Carlos Alberto Olano. He did some radio observations in L-band I think at the 21 centimeters is the 1.4 gigahertz. He used a 30-meter dish though, but he could pick up the collisions of comet Shoemaker-Levy 9. You can see the Jansky brightness of Jupiter is in single digits here, so the 20-meter can pick that up as well, I believe. That's kind of the lower limit on the 20-meter. These were, the observation on the left was one of mine I did. I thought I picked up Jupiter until I knew better. Jupiter's probably, well, it is right in the center, so I think this is, when I went back to it, I think this is very likely satellite interference. When I looked at the tracking profile, that particular observation is right around 1550. There's a lot of interference usually there. And another observation, here's of Jupiter. There's certainly a target right in the middle. I'm not sure if that is Jupiter or not. Jupiter, if you do pick it up in a larger scope, tends to be oval shaped because of the magnetosphere. So kind of inconclusive on that. On another one that I did, I thought, could I pick up a Jupiter storm? And this was kind of happening just before Jupiter went around the backside of the sun. So I couldn't continue. My own conclusion was it was inconclusive. But here on this particular one, I centered it on Jupiter, which is maybe that not so dark blue spot in the middle. I was hoping this might have been the IOA storm I saw. Now, this should not be confused with Radio Jove. Radio Jove is at a completely different frequency. This is an L-band, but there are some radio emissions from Jupiter during the storms that are in L-band. I was hoping to pick that up. And the Jupiter storms don't occur right on the planet. They are a bit off, as in this diagram you can see. I don't know how far off that would be, but I was hoping this might be it. So I went on, the Jupiter storm might last a couple hours. I did this observation of it. I picked up this. As soon as the storm was over, I had another scan. This whole object was gone. Whatever it was wasn't there anymore. I thought, well, is that some evidence? But another thing that happens, it's quite always frustrating, is the power in Kelvin change. So right here, dark Dark red is right around 57. In this particular thing, it changes more as the Jupiter was getting closer to the horizon. I think it was picking up the horizon effects more than Jupiter, and you can see that the power had changed. So I wasn't comparing similar things anymore. So inconclusive. I'd like to do a few more of these things. I'm not sure if it's possible or not, but it was something I wanted to try. And with a couple more minutes to go, let me see. Here's some advanced level observing of Jupiter with Dr. Reichert's paper. I've done some of the other Saturn observing. These are not necessarily mine. They're different observers. The first thing you do when you look, I guess a new person goes in, looks at the log, they see a Saturn observation, they look at it, and they see, wow, I picked up, or somebody picked up Saturn. That's not the case. Saturn would be center again because of the large field of view. I looked up, I looked at the profile for that. You can see that it's at about 1561, which happens to be the frequency transmitted by a Compass MEO satellite. So my conclusion is this was a satellite that just happens to be in the sky. They tend to be everywhere, and you picked up that. That's what that was. There's another Saturn observing. Again, more satellite interference, I believe, is what's in this area and not Saturn itself. Here's one of Venus, or Venus would have been center, but you've got this bright object here. The planets follow the ecliptic in the sky, and there are some things in the ecliptic. In this case, there's a galaxy, IC 443, supernova, not a galaxy, supernova remnant. I looked that up in a Cambridge radio catalog. It's also known as 3C157. If you go down here and in the L band, which I was looking at, that is 170 Janskis, which is fairly bright, and it matches those coordinates there. So I know I didn't get Venus. In this one I did on myself, this was an experiment I did. I knew I wasn't going to pick up Venus, but anyway, I tried. I was slewing back and forth on this along the right ascension. And you can see you pick up more of the ground effect that way. When I switched to doing, which you can do in the 20 meter, doing declination sweeps, you can see you get a totally different pattern as it goes higher in the sky. I think maybe it gives it time to cool off maybe, or maybe it's just the signal drift. I'm not sure, but I thought it was a very interesting experiment. Mercury observing, same thing. I think satellite interference from when I looked into this a little further. This was somebody else's post. Actually, this is mine, ST. Mercury been centered. This was something else. I concluded a satellite. This was, there's a few observation on Mars. I looked that up, and here we go again. It's that same IC 443, otherwise known as 3C157 again, along the ecliptic. That pops up a lot. And so my conclusion is, well, it's, I wanted to use a very wide brush. She was out there on the 20 meter for raster scans and how to interpret them better. And am I really seeing the target that either I was hoping to get or what others were hoping to get? And when I did a little digging, it's a lot of hydrogen one, a lot of satellites, a lot of imaging artifacts. And I think my last statement here is, if any of you are enthusiasts for observing in radio frequency radio frequency in the solar system, there was a contact at the Association of Lunar and Planetary Observers. I happen to be a member. Tim Robertson would be more than willing to help you with a podcast, whether it's Super Sid or Radio Jove or Radio Meteors or the Inspire or anything else. I did a couple podcasts with him in radio. I've got them posted on our analytical section page. I'll point them out tomorrow. But if you're inclined to do so, he would like to hear from you, and he can do that and post it. So with that, that concludes my presentation, and looks like I didn't go over too much time. Do we have time for questions?
Excellent. And I got one from Ed. He says, "How do you get planetary observing when you have to agree not to do that?"
How do you get planetary observing when you have to
Well, you're not supposedly not supposed to. You're agreeing not to do planetary, I guess, in your agreement. Is that correct?
Well, I wasn't sure what I could get with the 20 meter when I started looking at the raster scans. I was hoping that I could pick up some planets, especially through the years I saw observations on the planets. And some of these observations were by some of the scientists at Greenbank. So I said, well, if they're doing it, then they must be seeing it. But when I looked into them, it wasn't the planet at all. It was something else. So my conclusions then was I gave it an effort. I was hoping to get some planets with the 20 meter, but in the end, I concluded, well, within the solar system, you can just see the sun, the moon, and Jupiter, unless you've got a different set of input parameters or some kind of optical optimized. Some optimization software or other things that you can use.
I think
Steve, I think Ed's question was whether you sign an agreement not to look at planetary objects. And I think the agreement is you will not look at man-made objects.
Oh, I'm sorry. Oh, yes. That agreement was non-man-made objects. So that would be not tracking satellites. Now, I haven't done that when I had a target and, you know, a satellite just shows up. They're everywhere in the sky. But I think the reason for that is espionage, maybe. I mean, that's the only thing I can think of. Or listening in on, you know, communications. I'm not sure why they put that in there. But yes, that is man-made objects. You can't track them.
All right, a lot of kudos on the comments. So I want to thank you again, Steve. I've actually loved running the 20 meter, and you give me some ideas, maybe a couple of R tops that we can do later.
Okay.
Thank you very much.